Well, I'd like to welcome everybody to today's VLSI seminar. I'm Paul Penfield. I'll serve as your host to introduce the speaker. And then since I may have to duck out early, I've asked Professor Richard Thornton of MIT to cover the question and answer period in case I have to leave before it gets underway. Today's talk has two speakers, Bruce Edwards and Greg Efland. They're from Symbolics Incorporated. They're actually representatives of a rather large group of people, many of whom I believe are here in the audience, although I may be mistaken, who have contributed to the new microprocessor, which they've announced recently and which will be described in further detail next week at a special session at the International Conference on Computers and Design, ICCD, in Rye, New York. The title today is a 40-bit tagged architecture microprocessor that will be presented by Greg Efland. He's a native of Arizona and grew up in both Arizona and New Jersey, attended RPI to get a bachelor's degree and then got a master's at Caltech in 1980, and that was exactly the time when Carver Mead was getting his revolution in design going at Caltech. Very exciting days to be I imagine he'll look back with many fond memories on that particular period, which was so exciting at that time at that place. He worked with Craig Mudge there on a TriMOS bus with its support environment. In 1980, he went to Scotland to work at the University of Edinburgh and returned to the U.S. shortly thereafter to work at Intel in Aloha, Oregon. And then he was one of the founders and was at Sequent Computer Systems for a period of time. He joined Symbolics in 1985, and since joining at Symbolics has been working on this particular microprocessor. So I'd like to introduce Greg Efland. Greg?
When the phone is ringing, the light goes on.
So it's always useful, I guess, to start off with explaining some of the goals that we started out. Of course, we met them in the end. An overview of the architecture, which my main concern here, I guess, is to explain how this relates to the microarchitecture that I'm going to get into next. I also want to make some comments about the evolution of this machine from our current generation, some of the trade-offs that were necessary in this new technology. And finally, I'll end up with a short overview of our implementation technology. The first item here, I guess, is really more of a constraint than anything else, but as with many projects these days, we had a relatively small design team and needed to get the project done quickly, and that certainly had its influence on what we did. The main thing, though, is we started off with the idea of building a single chip Lisp processor. The current machines that Symbolics is delivering initially were based on TTL technology, and current machines are CMOS gate arrays. Certainly there's major price performance advantages with single chip implementation. This would basically allow us to build systems that were comparable to other standard microprocessor based machines. Another goal here was to increase our address space. The current generation is a 28-bit virtual address, and we've increased that by 16 times with 32 bits. For people who are somewhat skeptical about the need for that, we actually had to fix a bug in the current operating system in order to tape out this chip, so we're getting those extra bits, I guess, just in time. Some of these other things, I guess, I'll let you read. Another important goal we thought was the ability of the processor to run with standard dynamic RAM as its main memory and not to require an external cache for good performance. I guess we were successful, as this recent press release showed. Well, I guess I want to get into a little bit about the architecture of the machine. I guess the natural place to start is with memory words. As you can see, it's a 40-bit machine. Current generation is 36 bits. Of those, the bottom 32 store either an address or immediate data. And as it's a tagged machine, the next 6 bits are in fact the data type tag. And finally, we have a small field which is used for different purposes depending upon the objects that are being stored.
Greg, keep on talking now. They say that your mic isn't working.
And I'll show some examples of that a little bit. The one other comment I wanted to make here was with the representative data types, you can kind of look over those yourself. We also have a set of spare data types, and the machine works such that if you ever try to operate on one of the spare data types, that causes an instruction exception, and you can define in Lisp what the behavior for those data types is. These are some sample objects which are fairly simple and show the different classes of stored representation that we have. The first is just a small integer, 32-bit signed, and that's the immediate form of representation. There's other things like characters, for example, that fall in this class. The second is Lisp representation, and in both these cases you can see that the tag indicates the type of objects that's being referenced here. In this case, this is the address of the stored representation of the list. This being the first element, and this the second. You can see that when representing lists in memory, that these 2 bits, we normally call them the Coder code, indicate how to get the next element in the list. In this case, it says that the next element is stored here, and in the case of Coder nil, it says that that's the last element in the list. This is the third way we have of representing objects in memory, which is as structures. All of these objects are preceded by a header word followed by the actual bits representing the object. And in this case, this indicates this is a header, and the 2-bit field over here is used to indicate that it's a header for an array. There's other items which are represented in memory like this, and this distinguishes amongst them. In this case, we've stored the actual items in the array immediately after it. And one thing I wanted to point out here is that we can have different element types. For example, in this case, this is an array of Boolean elements. We could also have unsigned integers, for example, or characters, and that they can be packed into a word. We don't require that all the objects in an array be a full word in size. And so this is just a small array here. Normal array referencing instructions will actually do the right thing. For example, if you store into this a nil, it would pick out the corresponding bit position and store a 0 into that word. Now that we've briefly covered the data objects, I guess the next thing is to talk a little bit about stack frames and all. Ivory is a stack machine, and I guess in that regard looks similar to other machines that you might be familiar with. What I wanted to illustrate here is just a sample function that you might have and show what the activation record for that function looks like on our control stack. In addition, there's a set of pointers which are stored in the machine, and these are used to locate various regions in this stack frame. The first one is the frame pointer, which basically points to the first word in this frame, and there's a two-word header associated with every frame. I haven't showed the details, but this contains, for example, the return address as well as information which allows you to figure out where the start of the previous frame on the stack is. Immediately after the frame header are the incoming arguments, in this case, Old Peculiar and Guinness. And you see that we have an arbitrary number of words here. This is due to one of the features of Lisp function calling, which is a REST argument. And that says that the caller, when he calls this function, can actually supply an arbitrary number of arguments. And the callee, the function Firkins here, will actually put all of the remaining ones into a list. So the start of this first word here, where the function is going to allocate its locals, is variable and can't be determined until at runtime. And for that reason, we have this second pointer here, which is the local pointer. The final one is the stack pointer, which simply indicates the top item in the stack. And this moves up and down as calculations proceed in the function. I wanted to make just a few comments about Lisp function calling. We saw REST arguments in the previous example. There are several things here, I guess, which make function calling more difficult than in other languages, and I just wanted to kind of touch on these. People have an appreciation for them. As I said before, the caller is responsible for supplying the arguments in the way he wants, and in particular, he can supply a list of arguments which may need to be pulled out of that list when the callee gets them. It is the callee's responsibility to do that rearrangement. The other things, optional arguments, for example, you're not required to supply them, and if they're not supplied, then the callee will provide default values. The REST argument we saw in the previous example. And keyword arguments allow the caller to specify an argument by name rather than position. And just with those things done, the next topic is the instruction set. Basically, when the processor looks at a word in memory as an instruction, this is what it sees. There's two different forms of that. One is the full word, and the other is the half word shown below. If we start with this case, there's a 32-bit either address or data value here, and a 6-bit opcode, and sequencing code I won't say too much about. This is used mainly for literal instructions. For example, if you wanted to put an object reference to the symbol foo on top of the stack, that would be a full word instruction where this would be the address of that symbol. Another example of that would be one of the function calling instructions, where this might be the address of the function cell to indirect through. The majority of the instructions are actually in this other form, which are what we call packed instructions, 2 to a word. And essentially what we've done is we've reserved 16 of these opcodes in order to indicate this, so that we get 2 18-bit instructions in the bottom half, which we just arbitrarily call the even and odd half. And so the PC actually can point into the middle of a word. In packed instructions, there's 2 sub-formats. And both of them share an 8-bit opcode in the upper bits. most instructions are typically in the operand from stack format. And these instructions specify a single operand. It's not a pure stack machine. You get to specify one of the arguments directly. And that's typically done by putting the coding for the base register. Remember, we looked at the stack frames in here. And then this is simply an 8-bit offset, which gets added, or in the case of the stack pointer, subtracted from the base register to perform the to yield the effective address of the operand. The remaining operands, for example, an add instruction takes 2 operands, so the remaining operand would come off the top of the stack. The other option we have here is, instead of the operand being in the stack frame, it can be an immediate, in which case it's a small 8-bit immediate, and that's either signed or unsigned according to the opcode. Most of the time it's a signed immediate. For example, things like add and subtract, that's an unsigned immediate, which gives us an extra bit so that we can have essentially 8-bit values to either add or subtract. These are just a few sample instructions. I won't go through all of them. Kind of the normal pushes and pops that you would expect on a stack machine, as well as some Lisp-specific ones. Type member is a little bit interesting. That allows you to specify a set of data types. And this instruction is a predicate which excuse me, returns T or nil according to whether the data type of its argument is in the types set that you've specified. Instructions for accessing arrays, looping, as well as some subprimitives, which we'll get into in a little further on. Well, that's basically it for the quick architectural overview. I guess we've skimmed over a lot of things, but that's enough to move on into the microarchitecture register transfer level description. This is an older diagram, which I think was been somewhat sanitized to hide all our trade secrets, but it's still useful for getting an overview of things. The main data path is up here in the top, and that's fed by 2 memory arrays. The one on the top is a cache of the top of stack elements, and as you recall, we went over the stack frame earlier. We require that the entire frame for a function always be in the stack cache while that function's executing. And when you return for functions, if the frame is not currently entirely in the stack cache, it will go out to main memory and read the backup copies. Microcode also takes care of dumping that out to memory when it overflows. This is scratchpad storage for the microcode, and also contains a bunch of constants in ROM. The other important thing here is, in parallel with the ALU, we have data type checking and some hardware that does support for our garbage collector. The next section over here on the left, which we'll get into as well, is what we call the stack cache address module. And this basically contains the base pointer registers into the stack frame, as well as a separate ALU as just an adder and subtractor, really, for computing effective addresses into the stack cache. And this is a separate pipeline stage, as we'll see. The other important thing is to note that its controls can come from one of 2 places. It can be either specified by the microcode or come from the instruction decode PLA. Now, everything across the bottom here is basically associated with something that has to talk to the memory system itself. We'll look at this in a little more detail as well. This is really a separate address and data bus. We have on-chip ECC for the main memory arrays. And this was done for performance enhancements. Basically, we're able to check the ECC check bits in parallel with the normal tag checking on the data, so that we basically operate on the data uncorrected and then take an exception later if there's been an ECC error. These two buffers here are for temporarily holding data that's either arriving or destined for the memory, and in between that and the main data path. We didn't talk much about memory management, but this is a virtual address machine, and this is a translation cache here. Here's a data path with multiple PCs for different pipeline stages, and also an instruction prefetcher here. And the final thing is an instruction cache, which is small direct map cache. Primarily serves to buffer instructions that have been prefetched before they're used for execution, but it also holds small loops. This is a more detailed view of the main data path. Here we have the two memories that we had seen before, the stack cache 128 words and the scratch pad in constants. This is basically divided down the middle so that 32 of these are ROM locations. Important thing also in the scratch pad is that location 0 contains a duplicate of the top item on the stack, and that allows all the simple instructions to execute in a single cycle, because normally one of the operands is specified relative to a base register and is accessed out of the stack cache, and the top element on the stack is available in here. Most instructions also push their result back on the stack, and so when we write back, we normally write that both to this location 0 here as well as the stack pointer up here. In terms of timing, there's basically two phases in our cycle where things are happening. In the first half of the cycle, we access the registers and store them in these latches here. And in the second half, we do the calculation and store the result in this latch. There's 3 units connected in parallel. Of course, only one of them gets used on any given cycle: an adder-subtractor, full function unit, and a shift mask unit. This allows us to either extract or insert into an arbitrarily sized field at an arbitrary position in a 32-bit word. The other thing we have is a little bit of hardwired logic on the output. We store back into the RAMs in the next pipeline stage on the second cycle of the clock. And we have a hardwired T and nil here, which we can select instead of the actual result from the previous cycle. And this allows the predicate instructions to execute in one clock as well. The only other thing I guess I haven't talked about is this bypass path. If the result you're storing from the previous calculation is the same one that's being accessed on this cycle, then you read the right data instead of the actual data read out of the stack cache. So the normal forwarding there. This is the next module that I wanted to talk about a little bit. This is stack cache address, which is responsible for generating the addresses into the stack cache. This is done a clock cycle before they're actually used. We can see all the pointer registers here stored in this, what looks to be a register file. It's actually more of a hodgepodge than that. It's a bunch of discrete registers, and I've tried to indicate some of the other paths that exist. The reason for this, these are multiple copies of the stack pointer for the pipeline reasons. For example, this is a copy of the stack pointer at the start of an instruction, so that if the instruction fails, you can restore it, and the hardware's maintained the backup copy. The EA here is short for effective address, which is kind of a general purpose scratch pad location. Microcode normally puts the computed effective address of the operand in there, and it can select various sources then in the next cycle for being used as the address to the stack. The most common would be the EA as the read address, and most of the time the stack pointer is used as the destination. Some instructions, for example, an increment, would use this as the write address. And we also have a dedicated path to the frame pointer, which is used in function calling and returning. That's kind of the base side of this adder. The offsets, typically for the simple instructions, would come from the instruction register. Microcode can also specify a set of small constants. For example, if it needs to increment or decrement the stack pointer by 1 or 2, it would use this path here. We also have a path for getting these registers initialized from the main ALU, and it's not shown here, but there's also a read path which goes back into the main ALU. And the final thing which we saw in kind of the bigger block diagram is that normally this piece of logic, this data path here, is shared by 2 pipeline stages. And the initial cycle of any macro instruction, this is controlled by the instruction decode PLA. Further cycles, which may or may not be present depending upon how complex the instruction is, the microcode itself directly specifies these. One way of thinking about it is actually that the instruction decode PLA just is a copy of what would have been in the microcode ROM, but because of the pipelining, it's been moved back into this ROM here. And this is a very simplified view of the micro machine. I think Bruce got a little upset when he saw this, but the main thing I wanted to show by this was something which is, I don't know, not too common for microcoded machines. Basically, we read out several words in parallel and do a late select at the end on the current ALU condition. And so on this machine, we have 4-way branching, which selects on the current condition, so there's not a delayed branch, as is pretty common in most micro machines. In fact, we really end up reading out 8 words because of layout reasons, but conceptually we only support a 4-way branch here. So, in terms of timing, the first half of a clock cycle is used to select a new UPC, and there's various sources here. For example, you can repeat a micro instruction an arbitrary number of times. Start UPC comes from the instruction decode ROM to get you started. Microcode can do branches, and it can also do function calls and returns. One of the other interesting things with this, normally all the macro instructions essentially end up with returns, and when the hardware detects that the micro stack is empty, that return signifies that you should execute the next macro instruction. That allows you to use macro instructions as subroutines, microcode. Well, that's kind of what the registers look like. Next thing I wanted to get into is the pipeline. We have 4 stages, I, D, E, and C, which basically do what the comments say. The first stage in the first half fetches the instruction, and the second half decodes it. It's also responsible for computing the next PC. In the case of an unconditional branch, that's the target. In the case of most instructions, that's just the incremented PC. In the case of a return instruction, that would be the function, the PC one past the call that you're returning to. The second stage is the D stage. It does a couple things. First, the microcode ROM reads out the initial micro instruction for this macro instruction. The stack cache address does two calculations. In the first half, it computes the address of the operand typically, and in the second half, it adjusts the stack pointer to its final value at the end of the instruction. And we also resolve conditional branches in the D stage. The E stage is basically the main data path. Fetch the operands in the first half, compute result in the second. And in parallel with computing the result, we check the tags to make sure, for example, that the numbers we're adding are really numbers and not symbols or something like that. We also check to make sure that they're numbers which the hardware knows how to add. And this is the reason for putting the ECC on chip, is if the instruction is one that's referencing memory, we basically operate on the memory data uncorrected and in parallel check ECC. And we use the same exception mechanism as this. And then the C is the confirm stage, which is fairly simple. It basically just stores the result, or if an exception was detected in this calculation here, forces that exception. And this is just a simple example of that with a specific instruction, fetching a simple push. In this case, the PC is just incremented by a half word. Here we fetch the micro instruction. This 3 is just the instruction register's offset field, basically, that goes on to the offset bus and stack cache address, and push increments the stack pointer. The execute stage reads this operand out of the stack cache onto one of the operand buses, and the ALU just passes the result out. We also save the write address, since we're not going to actually store the result until the next cycle. And in this case, we use the stack pointer of the previous pipeline stage, since that's been incremented and points to the next location on the stack. And finally, we would just store it back here. And this is kind of a slightly more complicated version of that, showing several instructions in the pipeline at once. Just a sample function, which is invoked this way. This is meant to represent what that might compile into. The pipeline stages go across horizontally here, and time increases going to the bottom. It's probably a little different. I think a lot of texts have time going across on the x-axis. The one thing I kind of wanted to point out here was the two branch instructions. You can see this first branch is the first one here coming into the pipeline. And at this point in time, we're going to resolve this branch when it's in the D stage here. You can see that this predicate is computing the value, so that the value of this comparison is going to control the selection of the PC here for the branch. And of course, one of the operands for the greater P is being bypassed through the stack cache bypass path from this push. This branch is not going to be taken, so it takes a single clock cycle. When we get down to the second branch here, that condition is going to be true. And in that case, the branch goes here, and the hardware automatically flushes the instruction which is in this pipeline stage. And in this case, the branch microcode takes 2 cycles to execute. So this hole in the pipeline has time to get filled in with the target instruction, the push here. So the net result is that taken branches take 2 cycles and not taken are 1. I want to say a little bit about exceptions. In the previous example, everything succeeded. Of course, that's not always the case. There's various reasons that a microinstruction can fail in the execute stage. These are a few example ones. What the hardware does when a microinstruction fails is it has backup copies of all the execute stage state, which in this point is in the C stage, and that all gets copied back into the execute stage. The microinstruction, which is currently in the E stage at the time this one is faulting, its side effects are inhibited, and instead we force a new microinstruction to be looked up. According to the reason for the fault, different microinstructions are looked up at that point in time. In the case of an ECC error that's correctable, we'll simply re-look up the microinstruction which failed, and in the meantime, the ECC logic will have corrected the memory data for us and rewritten that in the memory data buffer. So the next time we retry the instruction, it will succeed. Invisible pointers are something that we didn't really talk about before. What they are is they're a special data type which indicates that the contents of a particular memory cell is not in the location that you've in fact read, but that it's forwarded to a new location. And in that case, this will trap to a microcode routine, which will essentially adjust the address register to contain that invisible pointer and then retry the memory read. For the paging system, we also support modified bit in our translation tables. And I also talked a little bit about some of the spare types that we have. This is an example of, it's kind of a spare, but we gave it a special name. In that case, the hardware knows how many operands the instruction takes, and it will force a branching to a microcode routine, which will cause an instruction exception with the appropriate number of operands for that macro instruction. And this is just a simple example of, in this case, an add instruction failing. You can see that once we've reached the C stage here, we realize that this addition that we did was incorrect. And in the next cycle, the hardware has copied back all the state of the add instruction back into the E stage. In this case, since there's a new macro instruction in the E stage, the hardware also had to copy that back to the start of the pipeline. There's no additional state restoration required since we're putting it all the way back to the beginning. And once again, this is an example of a data type that the hardware doesn't know how to do the addition on, and so that will trap out to a Lisp function which essentially emulates that instruction's behavior with those data types. So that's more or less it for the pipeline. One thing I wanted to conclude with in this section was just a short description of our memory bus. As I said in the talking about the goals, one of our hopes was to be able to use standard dynamic RAMs as main memory and get reasonable performance out of them. And this is the memory interface bus that we ended up with. It's really divided into two sections. In this set of pins, we specify an operation for the memory system to perform, and this is the address of the location to perform the operation on. The bottom set of pins are where the memory system, when it's ready to complete the transaction, actually does that. And there's the 48 bits, 40 bits of data plus 8 check bits for the ECC code, and 2 bits of acknowledge. These pins basically allow the memory system to specify when it's ready to complete the memory cycle. There's also a couple of other ways they can complete it. One is the normal way, but they can specify that the particular location doesn't have ECC check bits, so you shouldn't try to check that. Or you can also, for example, if the location doesn't really exist, you can say that there's some kind of a bus error occurred. The other thing we allow is an external master can essentially take over the upper set of pins and issue requests to the memory system just like the processor does. We expect memory to be four-way interleaved, although this isn't required. The processor, you can set a control register inside the chip, and it will run out of one-way interleaved memory banks. That might be used, for example, when it powers up, it's in that state, and that would allow you, for example, to run out of a boot PROM and then have that PROM copy itself into RAM before you actually really started running. And the processor can issue up to 4 requests before the memory system has completed any of the transactions. The other thing we do is we require the requests to complete in the order they were issued. Therefore, the acknowledge, I mean, you know at any point in time which request is being completed. And the chart on the bottom just shows an example of some bus cycles where time is increasing here to the right, and we're issuing requests sequentially, and they're completing according to the memory system's timing. So the arrows are here to indicate when a request completes. The first access is 0 and R is for read, and that completes on the very next cycle. This is the fastest the bus protocol allows any transaction to complete. The next cycle is a write request being issued, and you can see that the processor drives the data bus with the write data for as many cycles as necessary until the memory system actually acknowledges that it's received it. This kind of latency is what we expected as far as a typical memory system that you might build with DRAMs today. And the last thing I wanted to point out, RI is meant to indicate an interlock cycle. These are read, modify, write cycles that the bus supports for synchronization primitive. And this essentially locks one of the 4 banks that we're interleaved on. The other important thing is that we allow other requests to be issued during that cycle. For example, the instruction prefetcher could run here, or an external master could make use of that time slot if it wanted. So the next thing I wanted to mention briefly, I guess, is talk about what we had to do to make this machine, why we couldn't just copy the current generations. I guess the biggest thing that came up, when you started to think about it, was the sheer size of the microcode on the 3600. This is kind of a basic machine, and I guess extended versions of that are twice as many bits. This is what we ended up with Ivory. I think it's a little bit more than we estimated originally, but it still fits, so we're lucky in that regard. There are basically 2 things that we did to reduce the microcode from the 3600 series. The first ones were really the easiest. For example, floating point, we can always push that off onto one of the industry standard coprocessors, and in the memory bus we also have part of the protocol supports talking to those, so that was relatively simple. But the other thing I think is interesting is to minimize the penalty for using macrocode on the machine. One thing which may be a little out of order, we already saw that branching in macrocode is relatively fast. It's still not as fast as microcode branching, but it's only off by a factor of 2 in the case of taken branches. But the other thing is to really expose the resources that the microcode has access to macrocode. And the things that we particularly allow, one, the memory address register, which it itself has an auto-increment feature which the microcode uses, and we've allowed a mechanism whereby macrocode can use this as well. Also allow macrocode to specify the function being performed by the ALU, the condition select mux that microcode normally has control of, macrocode can control. And also the type checking on all the memory references can be controlled by macrocode. I have, I guess, 3 examples of that. These are some of the subprimitive instructions that we had referenced earlier. The first is a primitive for doing searching. I was told I had to kind of apologize for my C-style syntax here. But anyway, what this instruction does is it reads a memory location referenced by this address register, and the macrocode can load this register. It performs some operation that macrocode specifies on that and top item on the stack, checks a condition that macrocode has specified, and if that's true, it takes a branch. Otherwise, it just proceeds with the next instruction, and as a side effect, the address register is incremented. Now, recalling the pipelined memory bus, once the memory is actually streaming back data at 1 word per cycle, this instruction would execute in 1 cycle. So, for example, just by unrolling loops and putting these in a row, you can essentially search memory at 1 word per clock cycle. The second example is something for supporting bitblit. This is a little complicated. I won't go over it exactly. For those people who are familiar with it, these happen in parallel, so this is really the old value of the rotate latch, which is a special purpose register just for this. This basically allows you to take the data and align it onto word boundaries so that you can perform the operation on it, which kind of gets us to this particular instruction here for doing vector operations. I guess the important thing is all these cases is that the operation being performed is specified by macrocode instead of microcode. And they all execute in a single cycle. Finally, a little bit about implementation technology. It's a fairly vanilla 1.6 micron CMOS process. Those for the metal, the 1.6 is the poly, of course. This is where Ivory ended up in that. It's 12.6 by 12.3. And device counts, roughly 250,000 devices. Circuit design is pretty much fully complementary CMOS with the exception of the memories. And for example, the 6 transistor static RAM cells have the 2 N-channel access devices, which are not complementary, as well as the entire microcode ROM is programmed in N-channel devices. So that's where this big discrepancy comes from. And this is basically it. This is actually a photomicrograph of the first version of the processor, which was done in a 2-micron process, so it's not exactly what it looks like today. The main data path is this section up here at the top, along with some control logic down below. And you can see the 2 memories that feed it, the stack cache on the left and the scratch pad. You might be able to see the little boundary right down here where this half is ROM and the left half is RAM. So this is basically where all the work is going on. The big guy in the middle is the microcode ROM, I guess. All the bits had to fit someplace. This is the microsequencer, which contains the control stack, next microaddress selection, etc. There's a small data path section of that here, and then control logic. This is the stack cache address data path, which contains the base registers and the adder subtractor along with its control logic. And this is a large part of the memory system here. This interesting section here is, for example, the ECC logic. Down around in here are the instruction and PC pipeline registers, along with some adders and subtractors for doing branch address calculations. This is the instruction cache on the left, tag storage and instructions. And this is the address translation cache here on the right. I guess that's it. Any questions? Or?
Okay, do I have any questions? Incidentally, let me invite Bruce. Do you want to come down too and participate? He's our co-author. Bruce Edwards. Looking at the Bruce and Greg show. Any questions?
You had some idea what the size of the chip is and what the design goals are now, correct?
Yeah, that was.
The current chip as opposed to the earlier chip.
These are the current chip, which is the first revision.
How many pins did I get through total pin?
We're currently in a 144-pin package. I think there's probably about 5 or so spares, but.
And what CAD tools were used? Can you describe the tools that were used to put this together?
Yeah, I don't have a slide for that, I guess. We had a couple of simulators, one which was an instruction level simulator, which was used for porting software from our current environment onto the new architecture. We also had a register transfer level simulator, which was written in Lisp, and that performed a couple of functions. The first was it was actually the specification that the designers used to implement the modules in the chip. It also ran the microcode that's actually in the chip, so it was a microcode development tool. And we also have a way of using that to generate test patterns for the actual logic gates. So that was kind of the architectural side. The physical design was done with NS, which was actually one of the talks here, I think, last year.
Yes, we had talked about NS, the design system last spring.
And that is an integrated system which supports, the schematic capture and symbolic layout and simulation.
Bruce, do you have anything to add to
This guy's doing a great job. Could you give me an idea about the clock rate and cycle time?
Clock rate and cycle time?
Well, the current performance estimates are in the 3 to 5 times the 600 range. These are market numbers. And it's an 8 megahertz around that. The real answer is we don't, we're tracking technology, and as technology improves, of course, like every other semiconductor manufacturer, clock rates will move too. In comparison to other microprocessors, the clock rate isn't necessarily exactly comparable because, as Greg pointed out, some of the data paths cycle twice per clock cycle.
Are you making this inside, or are you going to a foundry to get this?
Well, we don't have fabs, so yeah, we're using a foundry.
Other questions about this talk?
Final chip route, is that part of NS, or did you use a separate tool for that?
What's the definition? You want to comment?
Well, we have used industry standard tools like the NS thing. It incorporates, for example, the standard cell blocks is using the Timberwolf router. But the top level chip route is done by our software and is integrated in with NS. The structure of NS is such that if there are tools running on a VAX or something like that, we can pretty easily integrate to them, and it works inside our test methodology. And we have a tracking system implemented in NS that tracks dependencies and tells you when you have to update and run and actually can run the programs on the VAXs automatically.
Could you say why you use this approach as opposed to using the approach like they used to work with the SPUR approach, which basically is a RISC-like architecture without microcode but with tagged hardware?
Now, this is the opposite of risk, isn't it?
Bruce first?
Well, I think there are some things that can be said about that. One is an important, there are some obvious, I guess, flaws in the spur thing. I don't want to say that in a negative way. That was put on top of a previous RISC processor, and they were attempting to change as little as possible in some ways. Compatibility with our current environment is very important to us, and also our current environment, some of the spur methodology was based on measurements of programs, benchmarks, which are typical of, well, I don't know what they're typical of Lisp programs, but those programs are atypical for our particular environment. And so since we were aiming at optimizing programs in our environment, measuring on our system, this was the approach we took. In addition, their system has requirements, for example, for cache and has certain memory system requirements. And because of the scale of some of the systems we wanted to make, we didn't want to guarantee or rely on the fact that there would be a data cache there and external caches for performance of the processor.
With that harder term was compatibility.
That's one of the terms. It's I guess yes, in the data sense and in the software sense. And plus, like I said, a lot of the function call support that Greg pointed out, the complex function call support, are exactly the kind of things that the spur work deems as relatively infrequent, which is not true in our environment. For example, a lot of, well, optional argument defaulting, rest argument passing. There's, as the cycle counts, for these are often not mentioned in the papers, and I guess in personal discussions with George Taylor, that was my impression of what
Well,
I mean,
one
I've
of the
heard
other
him-
comments is that the relative performance of those things is a much bigger span on something like Spur than on our machine, so that the penalty for some of the complex function calling or message dispatching is not as great relative to the base instruction set as it would be in Spur.
Did you get to do some field metering, or did you rely on expert intuition for that?
No, in fact, we did there is metering we've done. The other point I guess I wanted to make is that the Spur effort was willing to do a large software investment in the compiler. I think that's the other critical dimension that I didn't mention, which was they had already a compiler that was very good at register allocation and had done that basic work. And a lot of our aspect was to try to minimize the amount of software work, as you say, compatibility in that sense. So that was indeed a large factor for this machine being a stack machine is very close to our environment.
I might just remark that Dave Patterson will have his opportunity, because he's coming in the spring, to give a talk on the Spur project, and you can ask the same kind of questions to him as you asked to these guys. Is there another question or two?
Planning to be able to use just computers on boards and times?
I guess we really can't say too much. We've stated that we expect to have products using this technology in the second half of '88. And I guess, I don't know that there's much more we can really say.
Okay.
Excuse me?
Speed enhancement over the current technology.
Roughly 3 to 5 times 3600.
Okay, if there are no, well, I guess we got a question or two.
What took how many months? What did the project look like? Any surprises?
number?
Well, it's a little strange because the first revision of the chip was in some ways also used as a verification for the methodology, in that we had never pushed through a chip of the size of 250,000 transistors before. So some amount of the time, it's not clear that we would have done that particular revision if we had complete confidence in the tools and the methodology and the fab house. So there was a lot being debugged. That was probably a 6-month effort just to produce that chip, maybe 5 months just to do the foundry interface and testing for that. Do you think that's excessive?
Yeah, I think there was probably about maybe 9 months of on the front end of working on the register transfer level simulation, and maybe 6 to 9 months of actual design, that basically including both logic, circuit, and layout design. Maybe 6 to 9 months of actual design, that basically including both logic, circuit, and layout design to implement that.
The numbers of people are about, what, 4 or 5 logic designers, 2 or 3 architects, and about 6 CAD people.
Yeah.
Request for
Yeah.
test methodology.
In terms of the individual chip modules, originally the designer for a module wrote a small test suite to check it out, and there's a capability in NS to apply the same vectors to both the functional simulator, which is written in Lisp, and to the transistor description using RSIM, and to compare and make sure those are the same. So the designers were able to verify their small modules against the functional simulator at that level. The other thing we had was a complete kind of architecture verification suite, which was run on both the instruction set simulator as well as the functional simulator, and that served to check both the microcode, and in addition was a kind of a second way of testing the modules, in the sense that the designers didn't necessarily know all the exact interrelationships of the signals at their module boundaries, and so there was, occasional errors that were discovered at that level. That's basically
for functional, for fault coverage, that was done the old-fashioned way. So we did. I wouldn't say that we're home free on that. So a lot of the production testing hasn't really been handled.
What sort of clocking strategy using the logic? Was it all static? Or did you...
No, actually I had some other slides which people might be upset if I show them, but that's, for example, a register. We have 2 phases, non-overlapping clocks. This is a simple dynamic latch with a level restoring device here, and we also have a static latch implemented by this feedback, and you can break the feedback so you don't have to overdrive that when you writing a 1 in. Most of the logic itself is, with the exception of the registers and the memories, is fully complementary, and we occasionally used a static P device with the gate tied to ground as a load for wide OR gates. That's basically it.
Okay, if there are no more questions, oops, one more. Okay, let's make this the last question.
The accesses to the main memory? You talked about sort of 1 clock cycle as being...
1 clock cycle at 8 megahertz.
Okay.
So, in fact, if it was a 3 clock cycle time, that's 375 nanoseconds, which was, I think, reasonable.
So the throughput is 8 megahertz, and the latency would be like
Yeah, I don't know if I can find it. That's where the request is issued on one clock, and then 2 cycles later, the data arrives. Of course, in fact, in actual practice, the processor manages to keep the memory pretty busy, and so we really do see the full 32 megabytes a second in practice quite a bit.
Okay, I think at this point we'll close and you can come down and ask any more questions. Thank you very much, Greg and Bruce.